All right. So this is, we're getting into like how stuff really works. Internal resistance. So have a conversation.
It's the inverse of the slope.
I overview the slope of that.
I think it's B over I
Correct answer is B, 0.02. The slope is 50, but you need voltage over current for resistance. So inverse of the slope. So watch yourselves on the axes. Okay. So things that don't behave or obey Ohm's law are non-ohmic. So it's not a linear. It's not like that. Okay. Um, so this is just a random factoid. Ohm's law is not a foundational fact or foundational equation. Kirchhoff's loops rules, that's foundational. Um, you're going to ask me why, and I'm trying to remember why that doesn't work all the time. Maybe, okay, how about this? When we have a capacitor, charged capacitor charging an uncharged capacitor, that kind of, it doesn't work great. But Kirchhoff's loop rules work all the time. So, factoid. Okay. All right. Real batteries have resistances. We call it internal resistance. I don't know if you've ever tried to test batteries before, but if you ever test it with a voltmeter, usually they'll all, like, apart from the circuit, they'll usually say like 1.5 or 1.4 or something like that, which looks good, but a dead battery, so even if it's dead, it's still going to read like 1.3 volts or something like that. But then when you go to hook it up to a circuit, it's like, doesn't light the light bulb or whatever it's supposed to power. Um, that's because when you measure just straight away and it's not hooked up to a circuit, it's not, there's no internal resistance taking place. But when you have it hooked up to a circuit, you can see the internal resistance, and that's what's going to cause it not to work. Where this is coming from is we'll just say like the rate of reaction, what goes on in the battery chemistry of it. The more current, the more resistance is going to happen, internal resistance. Okay? So they'll say, here's your EMF. So the EMF, just to cloudy the water some more. So voltage, electric potential difference, electric or like potential drop, potential gain, electric potential drop, electric potential gain, like all those things kind of use, they're all in volts. Um, EMF is like the theoretical voltage across the battery. Okay. And then you've got, in a real case, you have current going through it. You got internal resistance. This would be the terminal voltage across that, like what's actually usable after the resistance. The internal resistance takes some energy away. Okay. So, because what we were assuming is these two are wired in series, so the current's the same. So across this, you're going to say the EMF minus the voltage drop from the internal resistance by current times resistance. Okay. So in a simple circuit, we're going to say the internal resistance plus the resistance of the resistor is going to have a total resistance of R plus little r. Good with that? Okay. So what is the value of the internal resistance of the battery if the voltmeter measures 8.5, so like your terminal voltage when it's wired to a resistor to a 9-volt battery. Okay. So we can do this a couple different ways, but I've given 17 ohms there. I know this is 8.5 volts across here. So that's a symbol of a voltmeter. Okay. See if you can brainstorm of ways to figure out the internal resistance. There are two ways that I'm looking at. There might be a third. Okay, one way would be, this is kind of like, I think what I would end up doing, just like quick and dirty, just like, come on, get it out. Let's get this. Okay, so I know across here is 8.5 volts. So across the big resistor, I've got 8.5 volts over 17 ohms. It's going to be my current of whatever that is. Why is my calculator not on the front top surface? What is it? Yeah, it is. Yeah, it is. Sorry, time change is killing me. All right, 0.5, and then I know it's in series, so the current here is 0.5 amps. The current here is 0.5 amps, and I know that if this whole thing is 9 volts, and that's 8.5, I know across the little resistor, it's 0.5 volts, 0.5 amps equals the resistance. So I find the resistance to be equal to 1 ohm. That would be probably the thing that I would do, just like if I was in a time crunch, like, go. Okay. Something that's a little bit more pretty, would be to do the loop rule of this. So you'd say, um, the EMF minus the current. Well, here, I'll do this. Voltage drop across the little resistor minus the voltage drop across the big resistor is equal to 0. Or you could do like EMF plus voltage gain, excuse me, is equal to voltage drop. Okay. And that, since it's all in series, you okay with that? Okay. And hmm. It's a good statement. I've got two unknowns. Hmm. Hmm. Well, I guess I could do this. So I'm not really incorporating the 8.5. I know that this is yeah. And that's what well stink. That looked pretty, but I've got two unknowns. I'm going to end up doing the same thing I did over here in the black. Okay, we'll leave it at the black. Okay, good at that. All right. Oh dear, shoot. Boo hiss. I feel like I should have come up with a better. You can chew on this while I chew on what I should have ended up with. Have a conversation about this question.
In the second half of class, this file
Do what?
not time change because of the time change,
Yeah, yeah.
We're all very tired, right?
Here we are. Okay, what do you say? Okay, so this is getting at the loop rule. If if this resistance decreased, the total current would go up. Yes. Okay. The current's going up. Um, Here, you don't know. Like, I don't know. But if the current is going up here, this is not changing. So the voltage across this guy is increasing. You okay with that? So you're using more energy, less energy is available outside the circuit, the higher that current is. Good? Okay. So if you ever have a battery tester, you may have a battery tester at home, see if it's good or bad. It needs to draw current in order to test to see if it's good or bad. Okay. Oh, look at me. Man, I should shut up and read my slides before I. Have a conversation. Okay, correct answer is there's a higher current. There's going to be a bigger discrepancy between your EMF and the voltage across the terminals because the current, as the current goes up, there's a bigger voltage drop from the internal resistance. Good with that? Toby.
Change it and keep the battery inside. Because if you like lower the current, if you raise the current, then the change between the battery gets bigger, right?
In the battery, yeah.
So wouldn't it be closer to the if they're both?
Good question. So what this is looking at, this is measuring your EMF minus that. This is measuring, so you have 9 volts minus the voltage drop across that this internal resistance took. Does that make sense?
Yeah.
Good question. Does that make sense? This is what's left over is the usable voltage. Okay, now this is like in mechanics, the internal resistance is like air resistance. We usually ignore air resistance unless it specifically tells us to include it. We're going to ignore internal resistance in a battery unless it tells us to consider it. Good with that? Okay. Oops.
Yeah, but the voltage of the battery is like theoretical voltage, like a 9 volt
Variable.
plus that doesn't change the grid system.
The only thing changing here is the only thing staying the same.
Okay. So no, the whole battery is like 8.5 volts. Voltage doesn't go down.
Correct answer is. Got 1 vote, 2 votes for C. Correct answer is Crazy Cats. Okay, I won. Where's my little cursor thingy? I see it on mine. Oh, I locked it. Yeah, it is frozen. Like legit frozen. Hilarious. Okay. So I1 is just through this. When you close that down, this is independently hooked up. It's in parallel. That does not affect I1. Okay. It does affect the total current. Yes. Okay. Now, talk to your neighbor.
There was no now there is the change that a different amount of voltage or a different amount
So similar.
I think it would be.
Yeah, what's a beam?
Because of the line of logic that I
It's like a beam.
What do you say? Okay, when it's closed, the total, like this is now playing a part. So in this loop, there's less voltage available to this guy. So the current in this is going to go down. Does that make sense? This is in series with this. So as more current goes through here, there's a bigger voltage drop across this guy. So that reduces the available voltage for that loop. Therefore, the current in here overall goes down.
But couldn't the battery with internal resistance just be like thought of as a perfect battery that has a lower voltage across it?
for a certain um, for a certain amount of current, yes. But this changes that perfect perfect battery, ideal battery with less voltage is going to change depending on how much current is being drawn out of that. So the more current that's drawn out, the smaller that perfect voltage, sorry, perfect battery, the smaller the voltage on a perfect battery will be. Does that make sense? So it changes dependent upon, so I would not necessarily go there because that kind of means there's a fixed fixed value of voltage.
In all these problems, we assume the wires are zero resistance unless otherwise specified.
Yes. Yep. Okay. Good. All right. Have a conversation. Correct answer is, here we go with B, parallel. What's the same in parallel? Voltage. Hence, we wire that up in parallel. Okay. Easy question. Ammeter measures current. Amps. I don't know why we call it an amp meter. I don't know why. Maybe some person who created the ammeter couldn't pronounce P's. I don't know.
I mean, technically speaking, what was the guy's first name? Pierre. Pierre.
Ampere. I don't,
Well, we don't even call the other one the voltmeter. It's called the voltometer. You're right. We could just call this an ampometer. Oh, that sounds kind of stupid.
Yay! Correct answer is A, series. So the current's the same, yes? Okay, easy questions. Here's a better question. Talk to your neighbor. Correct answer is B. When, when, come on, guys, you got this. You got this. When, when you are, um, when you're measuring anything, does not matter the science, even social sciences. Your your measuring device cannot affect or should not affect the thing that you're observing. Like, case in point, if Mr. Marshall came in and observed me, as much as he would like it not to affect the group dynamics, it would, right? Like, that is a poor example of a measuring device because that measuring device affects what you're measuring, what you're trying to observe. Okay, a better measure would have this, he would place this camera that no one would know. Okay? Wouldn't that be crazy if all classrooms were cameras and like your parents could pop on anytime?
Let's say hypothetically, Marshall student. Hypothetically.
It could.
What would you think about that?
What message would you like this student? Hypothetically.
Hypothetically speaking. All right, so
Write it down. I'm tweaking. It's an ammeter. Yeah, the ammeter has series.
I'd say it should be
Parallel, so it'd be like
I was one who was tweaking. That's my
it would blow the fuse.
okay, correct answer is E. Okay, so let's just for does that make sense? You got really low resistance. Okay, let's say just for kicks and giggles, it's just a wire. Okay, what we've created is a short circuit. Okay, in an ideal sense, this shouldn't affect this, but it does dramatically in real life. Doing this, that turns this off. Okay, and you've heard this statement like electricity or current takes the path of least resistance. I hate that statement, but it works really well for that. Okay, because uh, if I did this, this has more resistance than that. Which what?
Just use the word.
Yeah, it's just like, oh, all the current's gonna go through that. Like, no, it's gonna split up. There's gonna be more current that goes to that, but there will be current going through. Okay, so um, because a short circuit requires so much or allows a ton of current, that bumps up this internal resistance, the effect of the internal resistance, and so there's not enough voltage drop after the terminal to make that light up. Does that make sense? If this was an ideal battery, this would not be affected, but it absolutely is because of this. Good? Okay. Have a conversation.
You should yell that.
What do you say?
Amicable armadillos.
Okay. You don't want to affect the circuit. You don't want to have current going through here. Does that make sense? So you want a really high resistance. Griffin. You know what? That's a great question. It does.
Can we play higher or lower? 100.
I mean, we can. I don't know, but we could measure it pretty. We could figure it out pretty easily.
The price is right. The price is right. We did that with voltage.
Let me think about that. I don't know off the top of my head, but let me contemplate that.
There's like a wheel, but it's unfortunate. This one's definitely just. Well, you're not. I'm not seeing
Kilometer.
Wait. There's a lot of letters. I'm saying letters. But.
Okay, am I crazy or is the EMF?
What you do? Like a model battery.
Yeah.
So you just look at the battery.
Yeah, it's just like actually we see what resistance is reading and then look at what resistance is actually
The
there.
second one would be the EMF is just like
That's toast.
Right? Regardless of
see why that would be most resistant.
Delta V includes no, Delta V is the
I mean, the
difference
second
voltage
one,
from
why
one
you
end
do
of the
that
battery
really
to the other.
depends on whether or not it's being posted.
There's also
You
inside
need most resistance.
But what's
The
the EMF?
EMF is EMF.
EMF is the actual value
Which is
of
what
the
the
battery from
battery
the
or
inside
or
to the
actually
battery.
so it's
Neglect
like
stuff, like so it's like neglect the internals.
you know, like gas.
Okay. Correct answer is experimentally just take the battery straight away and hook it up to a voltmeter.
Oh.
Yeah.
And then experimentally hook it up to a circuit and then measure across the battery. Like apart or like with or without the connected to the circuit.
Is that for both or because wouldn't that?
No, so here's your battery. Just straight away you'd like one probe to the voltmeter. And then you just keep it like that and then hook it up to a circuit and then measure it. Same, it'll read something different because the internal resistance is happening on the inside.
So if you just hooked it up straight to the voltmeter, does that like ignore the internal resistance?
Because the voltmeter has a really high resistance.
That makes sense.
Okay? Good with that? All right.
So if I change it to I was thinking of
So good like lab setup question. Like that's just hypothesizing. I really sincerely am not hinting that you're going to see this, but you could. I mean, I'd say that was good. Like, hey, have you played around with these things? I don't know. Okay. Okay. Kirchhoff's loop rules on steroids. We use this when you have multiple power sources, multiple batteries. Okay, here's how you do this. We draw our circuit, and first thing we do is we guess which way the current is going. Okay, you're guessing. Um, if you guess wrong, it's fine. It's just the current after you calculate it is going to end up being negative. Okay? And then and you can do the junction rule for that one. And then for the loop rule, um, I'll just teach you. So if you're going in the direction of I'm just going to teach you. Okay. So here we have, bless you, we have a circuit that has two batteries. Okay. Because this is definitely in the realm of possibilities with circuits. Okay. Now, here's what you're going to do. You're going to first guess which way the current is going. Oh, I'm not going to do what I suggested I do. Okay. I'm going to guess that the current comes out of here. I'm going to say this is I1. Okay. That same current's going through here. It's still I1. Okay. Current's going to come out of here. We're going to say I2. I'm guessing this is the way it's going to go. And so down here, this is also current 2, I2. Lame. Here we go with that. At here, James.
Is there a reason we pick that direction for I2, or what's it just?
Oh, because it has to go through the battery. It's not going to go this way and that way. That's a one-way. Wires are one-way roads. Yes. Okay, you can't have current going two different ways in one wire. So at this junction, I've got current 1 going in, current 2 going in. Logically, I'm going to have current 3 going out. Okay, so current 3 is doing this. So you can either pick this junction or that junction, doesn't matter. So you have a junction rule. So we would say I1 plus I2 is equal to I3. The current going in is equal to the current going out. Good with that? All right, so junction rule. Now we get into loop rules. Okay, so what we're going to do is kind of like explore, traverse the path through a loop. Okay. If we start here, I'm going to start and stop here. So I'm going this way. Here, I go across a battery. Okay. This is a voltage gain in the way this is hooked up. Good with that? So I have a 9-volt gain. Okay. I am traversing across this. So I'm assuming there's no voltage drop across the wires. And then when I hit across here, I'm going, my path that I'm evaluating this is going in the same direction as current. So there's going to be a voltage drop here. This was a ladder. This is going to be a slide. And shoot some ladders. Get with that? Okay. The voltage drop across that resistor. So it's subtraction because I'm voltage dropping. That's equal to the current times the resistance. That's my voltage drop. You all right with that? Ohm's law, real quick, just, that's where I'm getting that. Okay, voltage drop across this battery, resistor. So I'm continuing, and I'm going across this one here. The direction of current's going this way, so I am voltage dropping across that. So I've got I3 times 2 ohms. And now I'm back to where I started. Okay, so all of that's going to equal to 0. The voltage gain equals the voltage drop, or I could just put it all on one side. And so that's that complete loop. I'm going to end up where the elevation I started. You okay with that? A lot of times they'll just do this for loop 1. Okay? Where is Mother Colors? Loop 2. Piece of junk, piece of junk. Where's my colors? There's my colors. Okay. Loop 2. I'm going to start and stop here. I'm going to go around this way. See if you can figure that out while I get another color. Get it? So you have 6 volts minus current 3 times 2 ohms minus current 2 times 1 ohm equals 0. How do we do? Okay. Okay, watch this one. How much time do I have? I'm pretty good, right? Okay. All right, so check this loop out. You're gonna learn some stuff on this one. Okay, I'm gonna do this loop here. I'm gonna start here, and I'm going to go around that loop. Okay. Okay, so I'm starting here. I got a 9-volt gain. I've got a current 1 times 3 ohm drop. Now, that brings us to here. I'm now traversing backwards across this battery. So this becomes a voltage drop. This is like climbing down the ladder upside down. I thought I was doing great. So this is -6. And then here, this is like climbing up a slide. I'm going in the opposite direction of current. Does that make sense? This is a voltage gain. Because current's going this way, I'm evaluating it this way. I'm going up a slide. So I have plus current 2 times 1 ohm equals 0. Okay? You'll have a expert TA
You gotta snacks.
at some point.
At some
What?
point, do you mean you're gonna assign it tonight and
Yeah, I'm
then none
gonna
of us are gonna?
It'll be assigned tonight. It won't be due tomorrow.
Okay.
When are we gonna have our first batch of for your? How late tonight?
As soon as you get enough stuff to be able to do it. Yeah.
Say that was an AP question, or like a question on your test. How much work do we need to show for that? Like solving that system equation. I just want RF.
Right. So,
No.
ask me that tomorrow.
I think you were.
It's a great question.
Smiley.
Yes.
You know, are you familiar with Kirchhoff accelerators?
I'm not.